Great. I want to take this as an exercise because when seeing this, let me see, let me put it here. I'm going to try to get the highlighter. Yeah, so you can see the mouse where it is located. And now, yeah, apply settings. Yeah, you should, just a second. Yeah, you should see right now. Well, in this exercise, there is something interesting happening with this, the calculation of a simple beam. Basically, we need to calculate or select, is the best word for this, a beam profile according to this table here that could withstand these loads applied to this beam. We have a point load of 10 kilonewtons, a distributed force of 5 kilonewtons per meter, and a bending moment at the end of the beam, which is in total about 11 meters. This moment is 10 kilonewtons per meter. Then we need to select the beam profile that could withstand these forces without yielding, basically. Then we'll write it here. So select beam profile. That's the first thing we're going to do. Uh, and the second one would be to estimate the deformation of the beam. Better said, estimate the largest deformation on the beam and see if that is larger than a certain parameter we're going to give or restriction we're going to give towards that end, meaning that it is pretty common for beam selection / design that you're going to have, okay, that the largest deformation should be, let's put it, the deformation of the beam, the largest one maximum, let's call it, has to be smaller than certain number here. And you're going to find these kind of representations in the literature, kind of L divided by 360, for example, meaning that you take the longitude of the beam and divide it by this number, and that's going to give you the maximum permissible deformation on this beam. This number, as it is formed, is pretty useful in the sense because you don't have to limit or specify a certain limit per each beam you have, because you can have beams of many length, type of length or different length, and this is going to be a general, let's put it in that way to represent the maximum deformation of the beam. Now, the question would be, where is this number coming from? Because it seems really kind of random in that sense. And it is not that it's random, there is certain specifications for this, and then you're going to find that, for example, for structural members, buildings and things of the sort, you're going to have some sort of representations dictated by the standards of construction of such structures. And on the other hand, if you are talking about certain other characteristics, for example, shafts, then you're going to have another type of determining that, which is also going to be determined by the standards. In any case, let's say the origin of these standards is on the structural side, meaning beam side. It is that people won't notice that there is a deformation that when they're walking on top of this structure here. Secondly, that any equipment that you're going to locate on top of the structure is not going to be visibly affected by the deformation of the beam, and well, things like that. In the case of shaft, for example, I mentioned that the deformation is going to be very dependent on what are the elements mounted on the shaft. For example, bearings have a very strict deformation restriction, meaning that the requirements for deformation of a shaft are way more exigent, are higher than for structural members. And the shaft you have, for example, install gears. It could be a compressor rotating at 60,000, 90,000 RPMs, which means that any deformation that you might have in a shaft rotating at such high speed would generate a tremendous vibration that would end up destroying the the whole equipment itself. So the requirements for shaft deformations are more higher, meaning very tight. They are not giving you any gap or slack in that sense when you are trying to kind of estimate or design a shaft. For beams, structural beams, they are a little bit more loose, let's put it in that way. But still, they are kept within, very nice tolerances. So for the exercise today, let's select the beam profile so it doesn't yield. And this has to be very much with the fact that stresses created because of these loads do not surpass those admissible stresses for this material, which is going to be about uh, the admissible or allowable stress according to this material for this IPE steel we're applying in this table is about 235 megapascals, right? And just to mention, this IP is a EU standard, European standards. You're going to find it like this. It's very common in these areas. But the procedure is the same for any other table as for use, for example, in United States or Latin America or any other country. Now we have this. We have okay, this other restriction, and then the situation that we need to validate why first it doesn't, stresses doesn't exceed the allowable stress here, and then the bending is because it might be possible that we select a beam, and that beam is, behaving nicely in the sense that it kind of withstand all the stresses caused by these loads here. However, when we try to calculate the deformation is that big that, even though it is selected according to the method we're going to be using here, functionally it's not, let's put it, good according to the deformation that is having. And then you would have to take actions to overcome that fact. And that action is it can be summarized in just increasing or selecting a higher or a larger beam, even though you know that, for example, let's say that in your exercise or your calculations, you think that the IP 140 is the one that complies with the beam profile selection we're going to do here, but it doesn't comply with the deformation you need to have. Then as an engineer, what you do is that you jump to the next one, and then you just uh, test that the deformation is going to be kept within limits. And if it doesn't happen yet, then you keep moving towards the larger, selecting a larger beam profile. And that's the way kind of is done. Great. I'm going to keep this table somewhere here. Yeah, let me open the, yeah, this one. Now, trying to keep the chat open in case you guys are asking something. Not this one. Yeah. All right. Now, first step is to determine the reaction forces appearing on those in these supports. Let me keep separating these. Let's do it. Let's put it in green. Reaction forces. Good. I have named this point here. There are points of interest: A, B, C, D, E, and F. And so we need to determine where are the reaction forces in the support V and in support E. I'm going to call them like this. Just a second. Let's see. I'm going to choose first to start calculating the reaction forces in support E. And to that end, I'm going to take moments about point B. we're going to have that. I'm going to take this force, this moment as positive, and this force as kind of as a quick calculation as negative. So follow along with me. So you can do it in the other way. That's not an issue. Just pick a sign convention for yourself, and you would go good. We're going to have then that this force is going to be minus 10 times 2, good, plus 5, this distributed load times the length of the load, which is 2. Then the point of application is going to be 3, basically, from this point to the middle of the point of application of the distributed force. And we're going to have this force here, which is going to be acting positively at 4 meters. Let me write it better. What is it? 8 VE. Perfect. And I'm going to need to add then this. It should be negative because it's a negative moment, and this is 10. And this should be equal to 0. I'll start preparing this. So this is going to put this in the other side. 8 BE equals to, I should start doing it right away. So minus 20 plus 30 plus 10 means that BE equals to, we're going to have here 20 divided by 8. And this is going to be about 2.5 kilonewtons. Let me put a red box here. Nice. Having now BE, I can take sums of all the forces applied here, and that sum of forces are going to be, let me put it here. It's going to be then minus 10 plus the reaction in B, that I don't know what is that, minus this distributed force, which is going to be 5 times 2, and that's going to be 10 again, and then plus this force BE, which is 2.5 kilonewtons. Then if you calculate that, that should give you BB, sorry. It's going to be minus 20, yeah, 17.5 kilonewtons. And I'm going to put again a box here. Good. Now, if I represent that here, because we know that the next step is going to be the creation of the shear moment and bend, shear stress and bending moment diagram. So I'm going to copy this one here because we're going to need this whole figure and to put it here. More or less at the same time. And keep separating this. And I'm going to kind of delete all of that because I'm going to substitute all of these with the forces. Right, so I'm going to have here blue a force here, reaction force, and another reaction force in point D here. Now, one comment about these reaction forces. So we're using a pinned support on the left and a roller support on the right, which by definition of a free body diagram, we are going to suppose that in here there's going to exist a natural force caused by any of this loading, which we're not considering here because there is no, or we're going to obviously, because this is not going to be representative for that. It might be close to zero. It might be that this moment is going to induce some sort of actual force on this. I don't know because we need to kind of construct the free body diagram to account for that. However, in this case, it's going to be pretty small. It's definitely going to be pretty small, and then we are not considering here. In this roller, there is not going to be any actual force generated as a consequence of a reaction because this beam is free to expand, let's put it in that way, in the horizontal direction. Now I'm going to draw here also some lines to construct the shear force and bending moment diagrams. I'm going to construct it in the interesting points, which are going to be this one here and and also this one. If I do it then more or less like here. Apologize if it's kind of a little bit slow the way I'm doing it, but I want just to show the whole process of this because when it comes to the part of the calculation of deformation is where the thing gets tricky. And let's also put the two horizontal axis for our forces. This one here for the shear force, maybe here. And also this one here for the bending moment. Good. I'm going to go over this in a way that is intuitive. So I have a 10 kilonewtons pointing down. That's going to bring me the diagram to this point. Then this is going to continue horizontally because there is no other force until it reaches the B support here. Then due to the B support, this is going to bring us up and it's going to cross this horizontal axis because it's going to be 17.5 minus 10. And I believe this is going to be a, oh my God, what does she want? This is going to be minus 10 kilonewtons. This is going to be minus 7.5 kilonewtons. Yeah. And then this is going to continue straight horizontally because there is nothing else here until it reaches where the distributed force starts. And we know that when we find a distributed force, what this is going to do is just, it is going to bring everything down. So it's 5 times 2. We are talking about 10 kilonewtons minus 7.5. So it has to reach minus 2.5. This is an error here. 7.5. This has to come down to 2.5. And then this has to minus 2.5. And then this has to continue straight because there are no other forces applied here until here to here, and then it goes to close at 2.5 in here. Yeah. When I was studying many years ago, my times, our teacher in strength of material, he really liked us to build shear stress and bending moment diagrams without any calculation, meaning the exams would be he would give us a loaded beam like this, and then without any calculation or anything like that, he would make us, just to present how the shape of the diagram would be. And they were one of the most horrible examples to give, because as you're not calculating, you don't know for sure if this is the shape it should behave or should have. But what I understood later is that it helped me a lot, because then when I started seeing diagrams like the loading, I could already identify what would be the shape of everything here. And that was something that helped me a lot. I didn't know that maybe it was his purpose or not, but it helped me a lot. But this is the way it's going to end up, this shear force diagram. What questions do you have? Great. Now, the bending diagram is a little bit more trickier, and because it depends on the shear force diagram, basically, let's remember that is kind of the integration of these. And everything goes fine until we find this kind of diagonal here. But, well, I did it already, and then you don't have to do it, but I suggest you kind of review this topic, because you already know him, know these topics, you have already studied it, but this is where things get tricky. And let me pick this color here. So moment starts at 0 here, and then they are going to grow like this until a point, maybe here. And this point is going to be 10 times 2 is going to be minus 20 kilonewtons meter. Well, here. And one thing, Shinji, if you can turn off your camera, because it consumes bandwidth and the recordings doesn't go fine. You have your camera on. Please, Shinji, kind of stop your camera. Then we have this other, okay, this grows in the same direction. These are this other area, and this area is going to come down to a certain point, and this is where it gets tricky. And this point, I'm not going to, I calculated, but I'm not going to mention it here. But when you have this type of diagonal, meaning that it's not a horizontal curve, what you're going to, when you do the kind of the integration of this, you're going to find out that this is a parabola. And this parabola, in this case, is going to do something like this. And bear with me, because it's already calculated. Great. Very close to 0 here. And then you have this other area, which is going to, say, increase 2.5 times force, that's 10. And that's going to bring me the moment from this point to this point, which is, I'm going to call it that this is minus 10. And there is nothing else applied in here up to here, where I have the applied moment at the end, which is 10, and then it cancels out with this one. And this is going to be the shape of this bending moment diagram. Right. Then one thing to identify here is that by simple inspection, it can be seen that the largest moment you're going to find in your diagram is this one, about 20 kilonewtons meter. And the problem would be kind of ending right now, in the sense, if we have if our task would be only to identify which beam, would work with this moment so it doesn't yield, but this is not the case. As for the reasons I mentioned before, that the beam can meet the criteria at the beginning, but for the deformation, it doesn't meet that criterion itself. Then I'm going to come maybe here to bring, now this is the time to bring the table. Then according to this bending moment diagram, the maximum moment is going to be 20 kilonewtons per meter. Now, what do I do with that information? I know that then I need to calculate what is the minimum section modulus here to use based on dividing this maximum moment and the inertia properties of the section. Sorry, the allowable, not inertia, just coming ahead, the allowable yield stress. Now, as a question again that was asked a couple of sessions about what was the meaning of this comes from, again, just to reemphasize, because maybe I didn't answer it correctly, not correctly, but completely last time. So this is a geometrical parameter, as I mentioned, and this geometrical parameter comes from the formula of the Euler-Bernoulli formula, where you know that the stresses caused by bending moment are related to the moment applied to the section, this parameter c, which is the distance from the central axis or the neutral axis to the end of the beam for our cases, which is where it's going to have the maximum stress, and this is going to be divided by the inertia of the section. Now, these two elements here form W. So W is the section modulus is simply a simplification of the formula by saying that this is this. But it comes from the Euler-Bernoulli equation for deformation of small deformations of beams, and that's kind of where this W is coming from. I hope that I complemented the information that I gave before. Now, if I continue here, I'm going to have that. This is going to be 20 kilonewtons per meter on the top. Then on the bottom, I'm going to have, now this is interesting. So the section modulus is presented in millimeters, and we're working here in meters. So what I'll do is I will transform everything to millimeters, so we have a direct result in here. And then the sigma allowable that I said at the beginning was 235 megapascals. When I transform that into kilonewtons per millimeter, that's going to be 0.235 kilonewtons per millimeter square. Now, I will also do this times 1,000 millimeters are equivalent to 1 meter. Then the minimum allowable section is, for our case, 85.11 millimeters cubed. Well, actually, it's going to be also, it's in the same format as this one, times 3 millimeters cubed. Now, if I focus on this part here, and I try, then I need to come down and shop for that part, meaning which is the section that has close to this one or larger. Unfortunately, this one here is not large enough. And this in here is larger than this one. Then unfortunately, I would have to choose this section here, which corresponds to the IPE 160. If you wanted to have let's say an average or something like an estimation, rough estimation of what your safety factor for yielding would be in this case, you can in this moment divide, just a roughly estimation, divide what is this, the material you are using, kind of this 108.7, well, times 10, 3 millimeters square, but just to keep the same scale, and then you divide it by this one, And that's going to give you more or less the approximate safety factor you're using for the problem. Now it looks good. So again, if the problem would be only to select a section that meets the criterion to not yield, so this would be over. This would be the end of the exercise. Now, let's check the most tricky part, which is the deformation of this. What questions do you have so far? None. Okay. Now let's apply Macaulay to calculate the deformation of this beam. Now we know that there is a bunch of loads here. We have 1, 2, 3 point loads, one distributed load, and one moment in this applied to this beam, meaning that if we wanted to apply any conventional method, such as the double integration methods, we will have to create several equations to partition this beam into this segment and analyze separately what's happening with the deformation in each one of these segments. Now, Macaulay's is an extension of the double integration method that allow us to have the full deformation range of a beam in just one equation. We don't need to take anything else into account. Just one equation that could be easily implemented in a software on a computer, and that you could have, the deformation graph or plot with just using one equation. Let's start with that. And I'm assuming that to start with that, I need to work on something with this formula. So I'm going to copy this graph again. And here is where it gets maybe complicated to understand at the first time, but we're going to sort it out. To put it here. Yeah. I'm going to name this 17.5, and this is going to be 2.5. Now, Macaulay says that, okay, we need to take, first, we need to make a section. And after we make the section, we need to take moments around about that section. And the thing with Macaulay's is that the section, it can be anywhere, but it is recommended that the section takes into account most of the forces applied to the beam. Then one of the preferable places to take that section would be this one here. So I'm going to make a cut in the beam here, and that means that I'm going to not consider this moment here, neither this moment here. And I'm going to also to put it a little bit better here. So I'm going to just get rid of this part of the beam, just to so we know that this is a section XX where we make the cut. Do you have any questions at the moment? Because deleting this moment seems, well, what about the effect of that moment on the deformation of the beam? So it is lost, or what happens? Do you happen to have that question right now? How could the deformation would be described in this beam if I just neglect some forces that are applied to it? Do you happen to have sort of a, let's say, concern or question there? Nope. Okay, great. I know that the length of the beam, I'm going to call it from the end of the beam to the cut, this is going to be X. Then I'm going to have another line here to locate the reaction in point B. I'm going to say that, okay, this is here. I know that these are going to be 2 meters, but the distance from this point to this point here is going to be X minus 2 meters. Let's now check the start of the distributed load. I'm going to have another line here. And this is going to be from this point to this point. I know that this is going to be 4. And from the start of the application of the distributed force to the cut is going to be X minus 4. Then I'm interested also in when the distributed force ends, but not because of the distributed force, because something that is the trick of all this problem. And let me draw another horizontal line here. So I'm going to have from this point to this point here, this is going to be six, sorry, and this is going to be 10, x minus 6. Finally, I'm going to have this line here, this reaction in point E, and I know that this is going to be from this point to this point, this is going to be 10, and this small part here is going to be x minus 10. Okay. But now, what happens here? So let me put the Macaulay's. We said that in Macaulay, kind of briefly, is based on functions that starts working once kind of at some point, meaning that if I do, and if I kind of analyze this from this point of view, kind of coming from the left to the right, and I see, well, at this point, 10 is acting, all the time. And then when I start analyzing this, maybe I use this one, analyzing this, when I come to these points, this, let's say, force starts acting or contributing to the deformation of the beam and stays like that on during that time. So Macaulay considers that once a term of the Macaulay's equation uh, is on, it remains on all the time. Meaning that when I come to the distributed force, when the distributed force is on, it won't turn off until the end of this. So it would just continue to turn on. This means that for Macaulay's, once you reach this length about x equal 4, this distributed force is going to be acting all the time. But hey, this is not the case because the distributed force is only acting on 2 meters of the section. This from here to here are 2 meters. But now Macaulay is considering, no, you know what? Once that term is on, that continues on all the time. But then that's going to give me an erroneous answer about the deformation. Yes, it's going to give you an erroneous answer. And then the follow-up question would be, what can I do to avoid this? The only thing you can do is that you imposed a distributed force contrary to the first one, but starting where the first one should end. Let's put it like this and move it a little bit down. Now, a force that didn't exist, you had to make it exist so you can account exactly for 2 meters of this distributed force. This is where the tricky part appears. And this situation happens with distributed forces. So it's pretty common to find this in distributed forces, that you have to do this quote unquote trick to account for distributed forces that are located in between the beam or acting in not completely on the whole length of the beam, but just in part of the beam. So this is the way to do it. Just add another force that is going to be contrary to the force of this segment that is appearing thanks to Macaulay's way of determining using functions to calculate the deformations on a beam. And the magnitude of this force is going to be also 5 kilonewtons per meter. Because you see, if this one cancels out with this one, giving you this only. Questions? When I cut this force, there is a moment or resistive moment appearing here. To call it mx. Because depending on that, when I make the cut, this moment is going to have a value. Next step is to formulate the equation of moments by taking moments of all these forces around or about the cut, xx. This is going to be, I'm going to consider this as positive, then I'm going to have that mx. Uh, let's consider the first one. This is going to be 10 times x. Now, this is interesting. This is not going to be written in any Macaulay's brackets because once, if I start counting the deformation of the beam from the left end till the end of the beam, this 10 kilonewton point load is going to be active all the time. So I can write this x without any Macaulay's brackets. So I don't get confused in that sense. Now I have this force of this reaction force on point B that is going to be acting at x minus 2 negative way. So this is going to be 17.5. Now I do use Macaulay's bracket here, x minus 2. Yeah. Then this force, this distributed force is going to be acting from this point here, and it's going to be acting the whole way around. So it's going to be creating a positive moment according to the sign convention I have just set here. And this is going to be then the force 5 times the distance, which is this one. So that's going to give me the magnitude of the force, x minus 4, times kind of the middle of this till that, well, would go kind of x minus 4 divided by 2 would locate me in this point here, and that's going to be the arm of the moment. And then what I can do is I can write that this as square and then divide this by 2. Then I need to consider this distributed force here, where this is creating a contrary moment. This is going to be a negative moment, and this is going to be in the same shape of this one, but it's going to be acting on x minus 6. So this is the arm of this is going to be the length used to calculate the force, and then the point of application is going to be in the middle of this. So it's equivalent to the previous one, but with these terms. And finally, I'm going to have this reaction force in E, 2.5 kilonewtons, which is going to be applied as negative also. I need to use Macaulay's bracket because this is going to start acting after 10 meters. So in this last part of the beam here, and this is going to be x minus 10. And all of this has to be equal to 0 because everything is in equilibrium. Questions so far? Everything clear? Good. Let me isolate the moment in x, or the moment in x, because this is equal to, according to Euler-Bernoulli, this formula here. Then this is going to be the same as, well, I'm just going to invert the signs on all of the rest of the terms here. Here, it would be minus 10 x plus 17.5 x minus 2 minus 5 divided by 2 x minus 4 square plus 5 divided by 2 x minus 6 square plus 2.5 x minus 10. Right. Then we have the first equation. To get to, okay, I got a very good question. It is why the terms in the parentheses x minus 4 and x minus 6 minus 6 got to the power of 2. Yeah, so let's remember that we are talking about distributed forces. And And this represents, let me put it here in red, or let's put it another one. Yeah. Let's explain it with one. So this represents the moment caused by the distributed force, right? And the moment caused by this distributed force is going to be the distributed force times the length where it is applied, that is 5 times x minus 4. So this is going to give me the force. Yeah. Then I have to multiply it by the point of application of this force, this distributed force, this one here, to take moments about the x axis. And the point of application of this force, when it comes to the case of uniformly distributed forces, is going to be in the middle. Yeah. So this is going to be the equivalent force of that one. So this is going to be 5 times x minus 4. Correct? Now, what's the distance between this central point or this, yeah, to this one here? This distance is going to be x minus 4 divided by 2. Then if I multiply this times this, I'm going to end up with this thing here. Is that clear? Let's wait for the answer. Okay, perfect. Great. Now I have the first equation, but it's not useful because I'm interested in y, not the second derivative of y with respect to x. So I have to, let's put it in the way, integrate twice. That's it. So if I perform the first integration of this, I'm going to end up with ai dy divided by dx. And this is going to be equal to the integration of this. That's going to be minus 10 divided by 2 x squared plus this other force here, or moment, 0.5 divided by 2 x minus 2 squared minus the integration of this term here. And this is going to be raised to the power of 3, and that 3 is going to multiply this one here, and this is going to be then 5 over 6 x minus 4 power of 3. Similar case is going to happen here. And the single case here over 2 plus an integration constant. And that integration constant is going to be called c theta. And it's called in that way because this term here I want to draw a rectangle and just this term here represents the rotation angle of the beam at that point. That's why it's called c theta. This is fine, but we haven't got to the deformation of the beam, so we need to integrate this last equation one more time, or integrate it because this is the first time we're going to integrate this. And this is going to be end up doing ai y equals to the integration of this term. This is going to be raised to the power of 3 times this is going to be 6. It's going to be minus 10 divided by 6 x to the power of 3. The same is going to happen in this case here. 2 to the power of 3. This term here is going to be raised to the power of 4. and then that 4 is going to multiply this 6, and then this is going to make 5 divided by 24, x minus 4 to the power of 4. The same is going to happen in this other term, minus 6 to the power of 4. And in this case, it's going to be similar to the first two cases, and this is going to be 2.5 divided by 2 to x minus 10 to the power of 2 plus, I need to integrate again this constant. This is going to be sigma theta x plus a second integration constant that we're going to call c sigma, and that sigma is because it refers to the deformation of the beam. Questions so far? Now, what is happening here is that I have two integration constants, and I need to find the value for those constants if I want this formula to work, and to find real numeric results. To find the constant integrations, I need to look for boundary conditions. And in our case, in this beam, our boundary conditions are pretty clear in the sense that I know that the deformation in this support B is going to be 0, and the deformation in this support E is going to be also 0. Then if I write that in terms of boundary conditions, it's going to be such that.
Sorry, there is a question
Yeah.
about the last equation, EIY. Maybe the lux part 25 divided by 4 instead of the 2 point.
Yeah, sorry. Yeah, that's true. This one here. Is it? Yeah.
Yes.
Okay, thank you. Yeah, that was, yeah, I need to do the same like this one. Good. Great catch. 6, 6. Yeah, thank you. Good. Then if I write my boundary conditions here, let's put start. I know that in X, in this support B, X equal to, the deformation is going to be 0. And also that in X equal, this point here is going to be 10, then the deformation is also going to be 0. Good. Nice. Let's apply those boundary conditions to those equations. So definitely these boundary conditions are referring to the deformation equation. So it is this one that I need to apply, not the rotation equation. I will copy this first equation to apply the boundary condition of x equal to 2. Here. Yeah. The first condition. Then what's going to happen that if x is equal to 2 and y is equal to 0, then this is going to be 0. And we know that any force that is after 2 is not going to be taken into account according to Macaulay's method, meaning that this force is not going to be taken into account at x equal to neither this force or this force nor this force here, because Macaulay says that the force gets active once it hits the point, or if the point you want to investigate for deformation is, at the point, well, after the point, after the force, actually. That's why it is used Macaulay's parenthesis here.
Hey, I think there is a mistake about the first part integration.
Uh-huh.
Yeah.
Where?
Because I think this is the 2.5 divided by 2, and you forget a square in the.
Yeah, well, you are very keen on that. Yeah, another missed. Yeah, that one. Great. Good. It's very good that you're catching those errors. Thank you. Highly appreciate it.
Yeah. So the next part is the cube.
Correct. Correct. Yeah. Great. Thank you very much. Then let me change this one. Yeah. Now, okay. I think we're good now. Then in this equation is going to be just, where should I write it in here? Let me write it in here. It's going to be minus 10 2 cubed divided by 6. Yeah. Then plus c c theta, better written would be 2c theta plus c sigma. And this is equal to 0. Then I can have an equation that is 2c theta plus c sigma equal to this. This is 8 times 10 is going to give me 80, 60, 40 divided by 3. Yeah. And this, I'm going to mark this equation. It's not giving me the answer, but I'm close to get the answer. Now, if I apply the second boundary condition, let me see if I can paste again. Yes. In here. And this is going to be when x equals 10, and then when y is going to be equal to 0. Now, these terms is going to be 0, second boundary condition. Yeah. Then this term is going to be active. This term is going to be active. Basically, if I try to find the equation, so any term that is before the mark of 10 meters is going to be active, and anything after that is not going to be active. So that means that this term here is not going to be active in this case. Now I can substitute everything, and that would be, mark it in blue, that minus 10 divided by 6, 10 to the power of 3, plus then x, actually 10 minus 2, that's going to give me 8 to the power of 3, minus 5 divided by 24. 10 minus, this is 6 to the power of 4, plus this term here. And this is going to give me 10 minus 6 is going to give me 4, power of 4. And again, I'm going to have 10 c theta plus c sigma. And this is going to be equal to 0. Now let me check for what's the answer to that one, because you can do it in your calculators if you wish so, and follow along and kind of compare if the results are the same. That would be nice. But I will just, for the sake of time, this is going to be reduced to the following equation. Let me just check search for it. Where was it? Yeah, going to be 10 c theta plus c sigma is going to be equal to 390. This one here. Question so far? Now, I have two equations, two unknown unknowns, and we need to work with that. And then I'm going to bring it here. So it's going to be, let me rewrite it in a way that is better to see. It's going to be 10 C theta plus C sigma equal to 390. And then I'm going to have 2 C theta plus C sigma equal to 4t divided by 3. And that's going to be about 4t divided by 3. That's 13.33. Yeah. Actually, I could convert this in a one, but it's going to be 13.33. And then you can subtract everything or these two equations, do a minus, a big minus here, and then you're going to end up with 8 C theta. This cancels out, and this is going to end up being there is an error here. This should be positive. Let me see. Shinji, could you please turn off your camera? Yeah, great. Thank you. Yeah. No, yeah, it's okay. It's 376.67. Then if you do the whole math in this, kind of, you're going to find out that C theta is going to be, in the end, 47.808, and C sigma is going to be equal to 80, minus 80.83. Okay, let's put a kind of a box on this one. Finally, we can build the deformation equation and the rotation equation if we wanted to. Yeah. Now we're going to substitute the value of those constants into this one. Let's call it deformation equation. And then the values of the constants are going to be plus 47.08 x minus 80.83. And there you go. You have the whole deformation equation in just one. Let's build a rectangle on top of that. Now, what's the next step? Well, we need to calculate what's the deformation at certain points. So what would be the advisable kind of points to calculate deformation here? So definitely, I would be interested to know the deformation at the beginning here, because it's where, let's say, the largest force is applied at kind of here at point A, which is x equals 0. I'm not interested in here. I might be interested in the deformation in between point B and point B. And I might be interested also in the deformation of this remaining part of the beam. So we have 3 segments of interest where to find the deformation and get to know where the deformation is going to be maximum, and where the deformation is maximum, that value, we're going to compare it to our constraint or restriction that the deformation should be lower, smaller than this value here, which is L divided by 360. Question would be, okay, which L, because we're working with supports and everything. So meaning that if we're talking about this, so you're going to have one L1, and that's going to derive at L1 divided by 360, or any other number that you're using for your design. Could be 180. And then you're going to have 102 here, Again, that's going to give you another, actually, we should write it at once. This is going to be kind of from this point to this point, you're going to have 8 divided by 360, 8 meters. So you're going to have the largest deformation in meters. And then in this case, it's going to be 2. And then this L3 is going to be 1 meter divided by 360. So if any deformation in this segment here is larger than this value here, then according to your criterion used to determine if deformations are okay or not, then you're going to say, no, it doesn't work because the deformation here is larger than here. And the same happens to the other segments that you're analyzing. Again, this could be L divided by 6, or it could be L divided by, sorry, by 360, or L divided by 180, depending on the case and standards used or requirements you need to comply with. Let's see what happens with the deformation. So when x equals 0, what's the deformation when x equals 0? So I could bring that formula again and say, well, the deformation when x equals 0 is, I know that this is not acting, even this is not acting because, it's 0. This is not acting, this is not acting, this is not, and this is not. The deformation is going to be end up being kind of correlated to the integration constant of the last equation. And if I keep working on this, I will have that y is going to be equal to this term, which was the only one left, divided by EI. E is the Young modulus of the material, and I is the inertia properties of the section of the material. Now, we're talking about steel, and that was not a information given, but we're going to consider E as 210 gigapascals. That if I transform this into a convenient measurement unit for our case, that's going to be more or less, how much was it? 2.1 times 10 to the power of 8 kilonewtons divided by meter square. Then I'm going to need I, inertial properties of the section, and that I is going to be tightly related to the section that you chose here, which is this one here. Let me put another color. I chose an IPE 160, and then the inertia properties of that are going to be this one here. That's going to be 8.693 times 10 to the power of 6 millimeters 4 to the fourth. I'm going to do this for you guys already, so we don't have to struggle with finding out things. So this is going to be equivalent to 0.869 to the power of 10, oh, sorry, times 10 to the power of minus 5 meters to the power of 4. Evidently, this integration constant is going to be related to, let's put kind of one note here. If you think about, okay, what are the units of this integration constant? This is going to be something like kilonewtons times meter cube. It's weird, but these are the constants after you do those two integrations in a row. Then when you put everything together, you're going to have that y equals to this C sigma, which was minus 80.83. And that's going to divide 2.1 times 10 power of 8. Then, another time series times 0.869 to the power of times 10 to the power of 5. And that's going to be end up being close to, how much was it? I have the value here. it was about 44. If I transform everything back to, this is going to give you something in millimeters, in meters, sorry, and that's going to give you something like minus 44.29 millimeters. So this should be 0 minus 0.004 something. And let me, and then that's the formation there. Now I took the time and put this in this formula in Excel, and just a simple Excel, I just put that formula in Excel, and it gave me something like this. Look at this. So this is the maximum deformation, obviously. It was found at this beginning of the part. You notice here as the constraint that the boundary was the boundary condition is meeting here, the boundary condition is being met here, and definitely this largest one is going to be something like 13 millimeters or something. Um, but the maximum deformation is going to be here, which is going to hit the 44.29 or 0.3 millimeters. Now, what do I do with this information? Well, I know that I have to meet the criterion of that this y has to be less than L divided by 360. And then this equals to, this segment is going to be L1 that we mentioned, and that's going to be 2 meters. And then if I'm working in millimeters, I'm going to say, well, 2,000, sorry, millimeters divided by 360. And that's going to be equal to how much? Let me do a fast calculation here. According to this is 5.5 millimeters. So what's happening here? So according to this rule, this is not being met. What does it mean? That the profile you have just chosen do not do yeah, does not do the work according to specifications related to deformation. What to do? What should I do? Should I modify something? Well, you don't have to do any other calculations besides selecting a different profiles, as we mentioned, and adding that profile or changing this term with the inertia properties of the new profile you are choosing, which most likely to be the next largest one, and then compare if this is going to be met or not. And you can give it a try to see when on up to when is that you have to be chasing profiles to meet the deformation criteria by just taking that term here and substituting that by these largest area profiles, like this one, and so on. So when you met the one that meets the deformation consideration, then you say you stop and say, well, this is my profile. Now, I did this on purpose to let you know that, yeah, even though you might have a very nice, what is it, just a rough estimation on how much is your safety factor in here. That is, let's put it in this way. If I do that calculation, it's going to be just that kind of as a value of safety factor. So divided by 85.11. So that's going to give me as a safety factor of 1.28. Yeah, even though it might seem like a nice safety factor, it it's not going to yield, but it's going to deform in a way that is not what was expected or was required from the problem or from the solution you are designing.